Hello everyone, welcome to my session. This is the first time I've been to Europe, and London is gorgeous. Firstly, let me briefly introduce myself. I'm Chenzhao, a big data engineer from Intel. I graduated from Zhejiang University in 2016 and joined Intel that year. Currently, I'm a contributor of Spark, OLAP, and Highbench. This session is divided into 3 parts. Challenges users and Spark SQL framework have met when it comes to complex SQL queries with very large data running on a large cluster. To deal with these challenges, we introduce adaptive execution. At last, I will introduce a few performance boost cases. The challenges. Number 1, an inappropriate parallelism on reduced side can degrade your query performance, but it's hard to make it optimal. There are 2 reasons. First, making it optimal requires manual efforts. A user has to first know some basic principles of distributed systems, then carefully tune it, maybe for multiple runs. Either too big or too small of this parameter, Spark SQL shuffle partitions, will make your query performance non-optimal. If it's too small, each reduced task will get too much data compared to its memory. Spill, even OM, will happen. While if it's too big, there will be more tasks, so more scheduling overhead, more I/O requests, and for the last reduced stage, there will be more output files. Secondly, even if it doesn't bother you to tune this configuration for each of your Spark application, the same reducer number can't fit all stages. For example, a stage close to the end of the execution may process less data than the stages in the beginning because of all the filtering, aggregation, and maybe inner join in the middle. Well, for these stages with less data, probably fewer reducers can increase the performance. Another challenge for Spark framework is join strategy selection. While planning physical plans, Spark chooses join implementation based on the estimated data size of each table. For example, if we want to perform a join, when one side is smaller than broadcast threshold, Spark will choose broadcast hash join. Otherwise, sort merge join. Because generally, broadcast hash join will perform better than sort merge join. But before execution, it's actually impossible for anybody to know the exact size of data produced by intermediate operators, because data can be so different. So, the most efficient join operator may not be used. The third challenge is data skew. Data skew means some partitions' data is significantly larger than the others. Therefore, these tasks will probably run much slower than the others. The poor load balancing will slow down the whole stage. Maybe will also slow down the whole query. There are some common ways to resolve this issue, but they all have limitations. Increase shuffle partitions. This will not work when most rows share one same key, because they will still be in single partition. increase broadcast threshold. This can bring more network overhead. Add prefix to the skewed keys. This requires many manual efforts, and this may not work if it's for intermediate tables. Before talking about adaptive execution, let's review how Spark SQL currently works and its limitation. A SQL query or a program using dataset data frame API will be analyzed, logically optimized, physically planned. Then we will get a tree of execution plan in the middle. This plan tree actually represents a DAG of RDDs. It's submitted to DAG scheduler as a whole. The problem is that this DAG of RDDs is settled in planning phase, and we can't alter our decision at runtime. We introduce adaptive execution, and I will illustrate how it resolves the issues mentioned. In general, adaptive execution tries to be more dynamic. If we collect runtime information of data and make new decisions beyond it, we may get a better physical plan and parallelism. In other words, we transfer control, like decisions of physical plans, parallelisms, from users and static to Spark SQL framework and runtime. To make this happen, we should do something both in planning phase and in execution phase. In order to take control at runtime, during planning, we cut the physical plan tree to multiple stages according to shuffle boundaries. We insert a node called query stage as root of each stage. Also a node called query stage input as leaf of each stage. This way, stages are divided before submitting to DAG scheduler, so that we can submit stages one by one and do some altering and optimization between stages at runtime. In the middle image, we can see adaptive execution version of execution plan has some more operators than the leftmost one, which are query stages and query stage inputs in the blue box. These two operators will make it possible to alter the sort merge join at runtime. This case, we will see in later slides. In execution phase, first let's talk about it in general. After depending stages are finished, we optimize the current stage's plan and parallelism based on fresh new data information, the statistics collected during shuffle write. Specifically speaking, first, we execute all child stages and collect runtime information. Second, we alter physical plan choice. Third, we handle skewed join. And the fourth, we dynamically determine the reducer number. We have implemented 3 features in adaptive execution, which are actually the steps 2, 3, and 4. Let's talk about them. To use this feature, you should switch on Spark SQL Adaptive Enabled. Besides this switch, there are 3 configurations. The default value works well for most cases, but you can still further tune them. Target input size for a reduced task. Adaptive execution will try to make the size of data processed by each reducer close to this parameter. This way, less possibility of wasting memory or out of memory. Then, min-max reducer number. Adaptive execution will find a best parallelism in this range. A concrete example for adaptively determining numbers of reducers at shuffle reduce side. We set input size for reducer to 64 MB, min reducer number 1, max 5. Then on map side, each map task will shuffle write 5 blocks because max reducer number is 5. Driver will aggregate the statistics sent by each mapper to get a total size of each partition. They are 70, 30, 20, 10, 50 megabytes respectively. You can see partitions 1, 2, 3 are relatively small. Even the sum is no more than 64 MB. Here, we do partition merging using a single task to process partition 1, 2, 3. Now, data is more even across tasks, and we have reduced some I/O. Second feature, outer join implementation at runtime. Student example. This SQL query intended to execute a sort merge join at the last operator. For the last stage, it will wait for its child stages to finish. After that, the statistics, including data size and row count of each partition, will be sent to driver. Driver finds out that the right join side is only 5 megabytes. It's small enough to be broadcasted. And because broadcast hash join generally performs better, mainly because shuffle is time consuming and it will reduce the shuffle. Therefore, the top query stage decides to alter the sort merge join implementation to broadcast hash join by removing some operators, like sort here, and also some setting in query stage input, telling the new shuffle RDD how to read data. This way, we have successfully reduced a shuffle, and we will have performance boost. The third feature. To use this, you should turn on the skewed join switch. Here, we use a simple algorithm for judgment of skewed partitions. And there are 3 parameters. They are skewed factor F, skewed size S, and skewed row count R. A partition is considered skewed if and only if its size is larger than median partition size multiplied by F, and also larger than a configured S, or its row count is larger than median partition row count multiplied by F, and also larger than R. Let's see how we implement this feature underground. In this example, we perform a join. Partition 0 of right table is much larger than the others, as you can see. Without adaptive execution, partition 0 will be processed by a single reduced task 0. Because of the large data volume it should deal with, it will run much longer than others, and the whole stage will wait for it to finish. Other stages which depend on this stage will also wait. A large fraction of the cluster's resource may be idle. In adaptive execution, partition 0 is detected as skew. We will perform 2 steps to achieve better load balancing. First, we split the giant task reduced task 0 to multiple tasks by adding more sort-merge join operators. Each task will still read the left table's partition 0 as before, because the left table is not too big. While for the right side, things are different. Instead of reading from all mappers, each reducer will just read data from a single mapper. Secondly, we perform a union on all the sort-merge joins. So actually, this is also a simple algorithm, divide and union, in order to provide better load balancing. About the performance, we have benchmarked adaptive execution on TPC-DS with 100 TB scale. No performance digression, 50% queries get more than 1.15 times performance boost. The max performance boost is 3.8 times. Here, I will also show some benchmark cases performed by other Chinese technology companies. Engineers from Baidu have reported 50% to 200% performance boost during their internal usage of adaptive execution. The boost is in 3 scenarios. First, certain BI scenario will hit the sort-merge join translation to broadcast hash join rule. This translation will hit this rule like joining several tables with filter strategy in subquery. Second, long-running application or using Spark as a service. This means starting Spark as a long-running server. For example, using the service of Spark like Zeppelin, Livy, or their internal SQL service, Baidu Big SQL. All Spark jobs originally shared the same shuffle partition number, which is not the best approach. So adaptive execution gets performance gain. Graph FM frame jobs. This also benefits from the adaptively determining reducer number feature. Actually, I'm not quite a graph guy, so here I will quote from Baidu developers report. Users have a 2-dimension graph with 1 billion edges. Using the connected components algorithm in graph frame, adaptive executions dynamically determining reducer number feature helps this. Alibaba has also benchmarked adaptive execution on TPC-DS 1 TB scale, with 1 master and 6 slaves. All the slaves had 32 cores and 64 GB memory. The overall performance boost is 1.38 times, and max performance boost is 3 times. And they have already incorporated adaptive execution in their cloud service product. Summary. We have implemented 3 features, which are adaptively determine reducer number, alter join strategy selection at runtime, and handle skewed join at runtime. Actually, there are more potential opportunities here because adaptive execution provides a runtime optimization framework. For example, you can write an optimization rule just like the join strategy alteration rule. The community is reviewing our code. Maybe it will be in Spark 3.0. The code is open sourced at Spark Adaptive Repo under Intel Big Data. We welcome collaboration. Thank you very much.
I'm not sure if, thank you for the talk, first of all. I'm not sure if you mentioned whether it is already released or this is ongoing work where it would be merged into Spark. How does it, what is the schedule there?
Sorry, I didn't get, you mentioned adaptive execution is our only work or what?
Because those are features that you develop at Intel from what I understand.
The 3 features are what we implemented now, and there can be more. Yeah.
No, he wants to know when they're going to be available.
When will it be in 3.0?
When could he use it? 3.0?
Now he can use it because it's open sourced. You can just find that. Yeah.
So the feature seems to be amazing, but from one parameters now you turn to different parameters that you have to tune, especially the skewed join like F, S, and R. Can you tell anything about how to come up with those numbers?
Actually, that's a very good question because that feature actually is not very easy to design an algorithm that fit for many cases. So we actually here, we have designed a very simple algorithm. Yeah, so if you use this feature, maybe you should tune it yourself, and you can check in your UI, you can see how many times are your skewed partition, like the size, the row count is divided by the median. Then you should tune it. Yeah. Thank you.
Thank you for the talk. How does adaptive execution handles the exchange reusage, having in mind that the physical type of the join changes in runtime?
At runtime, before that, I didn't get it very.
Okay. How does adaptive execution handles the exchange reusage? Spark can reuse exchanges.
Spark user what? Scientist?
Can reuse exchange and exchange shuffles. Can reuse a shuffle of a table.
Sorry, I still didn't understand. Sorry, my English listening is not very good.
So you wanted to see how does adaptive execution handle the exchange reusage? How does adaptive execution handle exchange reuse?
Oh, exchange. Oh, yeah, good question. actually we have exchange reuse. If you see in query execution, we have an adaptive preparation compared to with the original preparation. And in that adaptive preparation, we simply add a rule called plan query stage. And the reuse exchange you mentioned is actually incorporated in that rule. So you don't have to, for example, one exchange actually execute many times. You don't worry about that. Yeah.
So how intrusive are the changes for this? Is it an easy change to incorporate into Spark in terms of just the code changes, the structure of the design of Spark, or is it something very, very complex in terms of code changes? No, in terms of a patch, basically. And maybe the second follow-up question basically on top of that is that is there something that can be done in Spark to incorporate such changes much easier?
Oh, I understand your question. Actually, it's not very complex. Actually, if you think about the core idea, it's quite simple and it's very good. Actually, Spark originally had the submit map stage API in DEX scheduler. Yeah, this is written by Matei long ago. Yeah, actually, we take use of this API here. So you can say it's not far from current Spark, and it's not complex. Yeah. Okay, you're welcome.
Can you please re-explain the example on slide 14? So the one where we had repartitioning. So when we decreased the number of partitions, can we just check back this example? On slide 14.
Slide 14, okay.
Yeah, so here I don't really understand what yielded a better performance. So when we adaptively determine the number of reducers, so I didn't understand like the whole idea here.
Okay, I think I can. You mean I explain this a little more?
Yes, please.
Okay. After map size drop, after the reduced side, each mapper will send the statistics to driver, telling the driver, my block 0 maybe have 5 MB, my block 1 have 2 MB, this kind of thing. And then the driver will do the aggregation. It will plus all the mapper statistics. For example, then it will get to know block 0 is 70 because block 0 for mapper 0 to mapper n, the sum is 70. And after this, the driver can make new decision. It will, first, the principle is that it tries to make the ultimate reduced tasks, the data size of each task processed, close to 64 MBs. So for partition 0, it's a little bit difficult to split this. It's already larger than that. So just this one will take a reduced task. Then we move on. Partition 1, 30. Okay, very good. Partition 2, 20. Then we got 50 here. Still not greater than 64. Then partition 3, 10, plus the previous sum, that's 60. Now, then actually, Spark will try to add 60 to 50, which is partition 4 size. Then find, oh, I can't add this partition 4 to the task 1 because it will be too much. So stop here and start a new reduced task for partition 4. Okay.
Hi.
Hi.
I'd like to
ask about the join skew avoidance.
Okay.
So, can it deal with a situation where both sides have a large partition on the same partition, or if there's different large partitions on either side?
Yeah, very good question. Actually, if the two tables are both skewed, we have to do something like Cartesian. Yeah, join partition 0 on the left. Let's take this example. Left table has two partitions, partition 0 and partition 1. No, maybe not right. Left table has, we have two mappers. And, okay, it's difficult to, it's something like Cartesian join in the case that only right table is skewed. The left table, we don't need to care because the union will solve anything. But if the left is also skewed, we should, after split it to multiple parts, each part join with right sides each part. Then we got an n multiple by n, a union of n multiple by n Solomon joins. This way, it will be, the answer will be correct. Yeah. You're welcome.
So this optimizations currently only talk about joins. Do you think in the future something like this could be used for co-grouping?
Yeah, I think there are so many possibilities, but I don't understand deeply of maybe many operations you mentioned. But I think maybe you can check our code on GitHub, and you can see in your real cases if this rule can, if your code group you think this can. Maybe this can incorporate it in adaptive execution. Just take use of the statistics and do some altering, optimization. Yeah.
Okay, that's all the time we have for questions. Thanks very much.
Thank you.